Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 7 of Algebraic Topology. Our today's topic of discussion is fundamental group, and on a related topic we will study what are simply connected spaces. So why we need fundamental group? Because fundamental group provides a background to study another functor of the category of topological spaces. So far we have studied only one functor, namely pi naught. So it's a functor from the category of topological spaces to the category of sets. So if you remember, if I have a topological space X, then pi naught of X will give me path connected components of the space X. So for example, if there are three path connected components, x1, x2, x3, then pi naught of X is equal to x1, x2, x3. So these are the objects, and similarly we also studied what are going to be the images of maps. So if F is a map continuous function from X to Y, then what is going to be pi naught of F? So it takes path connected components of X to the path connected components of Y. So now fundamental group is a topological invariant. So if two spaces are homeomorphic, then they have the same fundamental group, or in other words we can say that if two spaces have different fundamental groups, then they must not be homeomorphic. So this fundamental group is going to provide us the background for another functor which we are going to study in our next discussion. So precisely we will only study fundamental group in this lecture, and we will see what is this functor pi1 in our next lecture. So what is the main idea of the fundamental group? So the main idea of the fundamental group is to understand topological properties using loops contained in them. So what is a loop? So a loop, we will see precise definition. So I can say that if I have a space, let's say a sphere, then a loop is basically just a simple closed curve. So in other words, a curve which looks like this. So this is a loop. Now if you see that if I have two loops in a sphere, then I can continuously deform this loop to this inner loop, and of course I can keep on deforming unless this loops become just a point. And similarly, if I take any other point, then the same thing happens. Any loop can be deformed to just a point. So this is the property of this sphere. But if I take, for example, this torus, then if I take, for example, a loop which goes like this around the torus and comes over here, so this loop cannot be deformed to a point, just like the case of the sphere. So this loop is special in this sense. Similarly, I can have another loop, for example this loop, and I cannot deform this loop to a single point. So in other words, there are two loops which cannot be deformed to a single point, and in the case of the sphere, every loop can be deformed to a single point. So by just studying the loops, I have come to know the difference between a sphere and a torus. So that's the main idea to study the fundamental group. Okay, so basically we are discussing the topological properties, but using these loops, and these loops will form a group, so which will be called fundamental group. So let's start with the study of loops. So how do we define loop? A loop in a space X is a continuous function f from I to x, where I is equal to the closed interval 0 to 1, and f of 0 is equal to f of 1. The common starting and ending point f of 1 or f of 0 is called the base point of the loop. Okay, so for example, if this is the space X and this is the interval 0 to 1, then what is a loop? A loop is a continuous function from 0 1 to the space X, So let's say this is the point f of 0, and we can go on and we will keep on getting points. So for example, let's say this is f of 0.2, this is f of 0.4, up to so on. So as we move on this interval, we are getting points on this path. So there is another condition apart from that f is continuous. There is another condition that f of 0 should be equal to f of 1. So if we keep on moving, so f of 1, okay, so let's say this is f of 0.5, this is f of 0.75, up to so on, this is f of 0.9. This point is once again f of 1. So f of 0 is equal to f of 1. So in other words, the point where we started from should be our ending point. So this is a loop in a space X. So let's consider an example. Let x be R2. The following function f of t is equal to cosine 2 pi t sine 2 pi t, and here of course t belongs to the closed interval 0 to 1, is a continuous function, okay, and f of 0 is equal to 1, 0 is equal to f of 1, hence f is a loop in R2. So this function is continuous. Of course sine and cosine are continuous, so that's why this is continuous. And why it is a loop? Because we can calculate f of 0. So let's see what is f of 0. So f of 0 is equal to cosine 2 pi into 0 and sine 2 pi into 0, so which is basically equal to cosine of 0 and sine of 0, and we know that sine of 0 is 0 and cosine of 0 is 1, so this becomes 1 0. Now let's see what is f of 1. So f of 1 is equal to cosine 2 pi and sine 2 pi. Okay, so we know that sine n pi is 0, so basically sine 2 pi is 0. Cosine n pi, so we know that cosine n pi is equal to minus 1 raised to power n, so this is basically 1. So once again we have seen that the starting and the ending point of this function is the same, so and also f is continuous, so this is a loop in R2. Okay, similarly we can define many other loops. Now given two paths, okay, such that the ending point of f is equal to the starting point of g, that is f of 1 is equal to g of 0, we can define a path which is basically the composition of the path. So basically if f is a path, so in general this discussion will be applied to loops as well, but in general we are trying to see how to compose two paths. So for example, this is a path f, and this is the starting point which is basically f of 0, and this is the ending point which is basically f of 1. And let g is another path such that the ending point of f and the starting point of g are the same. So in other words, this point is also the starting point of g as well. So this is g of 0, and this is the ending point of g, which is g of 1. Okay, so normally we take a path f to be a function from I to space x, and similarly g is a function from I to space x. Now if this condition is satisfied, that f of 1 is equal to g of 0, then I can consider this whole path as one path. Okay, so I can consider this red line as my new path. And how to define this mathematically? So basically we divide the interval I into two portions, so from 0 to 1 by 2. So when t varies from 0 to 1 by 2, we have this function f of 2t. So basically this portion is 0 to, so when t varies from 0 to 1 by 2. So as I move t from 0 to 1 by 2 I'll be getting points of this f, and starting from this point I will reach this point. And from 1 by 2 to 1, okay, so basically from this point to this point, so t varies from 1 to 1 by 2, I'll be getting points of g. So basically I'll be moving along this path, and basically when t varies from 0 to 1 I'll be getting this whole path, which is basically you can say composition of f and g. So why f of 2t and g of 2t minus 1? So if you observe that if I'm taking f of 2t, then when I vary from 0 to 1 by 2 I'll be starting from f of 0, because when t is equal to 0 this is f of 0, and when t is equal to 1 by 2 then f of 2 into 1 by 2 is equal to f of 1. So basically when you reach t is equal to 1 by 2, then you reach this point, so basically the end of the path of f. Similarly in this case, when t is equal to 1 by 2 in the case of g 2t minus 1, so let's see what is g of 2 into 1 by 2 minus 1. Okay, so this is basically equal to g of 0, because this 2 cancelled out with this, so 1 minus 1 is 0, so g of 0. So in other words, when t is equal to 1 by 2, this will give me the starting point of the path g, and similarly when t is equal to 1, so let's see what is g of 2 into 1 minus 1. So basically this is equal to g of 1, so this is the end point of the path. So in other words, when you vary t from 0 to 1 by 2, you move along the path of f, and when you vary t from 1 by 2 to 1, then you move along the path of g. So basically we have taken two paths and we have kind of composed them in this way, that first you travel along f and then you travel along g. Okay, so this f star g, which is the operation that we just defined, is a continuous function. Okay, so f is a continuous function, g is a continuous function, and what about the part where these two functions are equal? For example, so t is equal to 1 by 2, so f of 2 1 by 2 is equal to f of 1, and we know that f of 1 is equal to g of 0, and which is equal to g of 2 1 by 2 minus 1. So basically at t is equal to 1 by 2, these two functions are equal, so there is no gap between them, so they agree on this intersection. So this f star g, if f and g are continuous functions, of course these are continuous functions because these are paths, and paths are continuous functions, so f is continuous, g is continuous, and they agree on this intersection, so that's why we can say that f star g is a path, because it's a function. F star g is a function from I to x, and it is continuous, so it is a path in x. If we consider homotopy class of paths in a path connected space, then it is trivial. So far we know what is a homotopy of two functions, and in a path connected space any two paths are homotopic. So this makes our discussion very trivial, because we are going to see if a space X has paths. So in particular we are going to see if they have loops, and we are going to study loops up to homotopic. Okay, so for example, two loops are same when they are homotopic to each other. So if you remember, we discussed that we are going to see that if one loop can be deformed into another loop, so this deformation is basically going to be defined mathematically in terms of homotopy. So in other words, I'm going to take homotopy classes of loops, but if we consider the homotopy that we have already discussed, then according to this homotopy, any two paths are basically homotopic in a path connected space. So path connected space is not a very strong condition. So in other words, if I impose a very small, very mild condition on my space, that space is path connected, then any two paths are going to be homotopic. Okay, so which is not a very good thing, because then I will only get trivial groups. Okay, so for example, if I'm discussing the homotopy classes of loops in a space X, then this is always going to be a trivial group, so which will not give me any structure of this topological group. So now we are going to generalize the idea of homotopy in the following way. Okay, so let A be a subset of X, and F0 and F1 are two continuous maps such that F0 restricted to A is equal to F1 restricted to A. So we define F0 homotopic to F1 relative to A if there exists a continuous map F such that F is homotopy, and so this is the extra condition that we are going to impose here. So what is this condition? So this condition says that F of AT is equal to F0 of AT is equal to F1 of AT, F1 of A for all A belongs to A and T belongs to I. So in other words, so far we have seen that if this is a function F, and this will be homotopic to F0 if one, so this function F can be deformed to F0, so somehow something like this. So this F can be deformed into F0 if there exists a homotopy F. Okay, so there was no condition, there was no extra condition. Now we are going to impose another condition on the homotopy. So what is this condition? So first thing is these two functions have this extra condition that F0 of A is equal to F0 restricted to A is equal to F1 restricted to A. So for example, it will look something like this. So this is F and this is F0, and this small portion is basically the portion where they agree. So these are the values of F of A which are equal to F0 of A. Okay, so this is the extra condition. So we are basically not considering any two functions, but the functions which agree on this set A. And there is another condition on this homotopy, is that for each and every T, its values are the same for all A belongs to capital A. So in other words, when we deform this F to F0, then let's see, these are the intermediate functions, but the point is for each and every value of T, they are going to agree on the points of A. So so let's say I have F of 0.5. So let's say this is the function F of 0.5. So as T belongs to I, so we are moving from this function F0 to F1. So for example, an intermediate function if T is equal to 0.5 is this function, and of course when this X varies, then we are getting points on this path. Okay, but the important point is they all agree on this portion, which is the portion of A. So for each and every value of T, this F of AT is equal to F0 of A is equal to F1 of A. Okay, so they all agree on this small portion. Okay, so that's the relative homotopy. So the original definition of homotopy may be viewed as relative homotopy with respect to A is equal to 5, because this A is empty in this case. So we will call our original definition, the definition where we started from, so that definition of homotopy will be regarded as will be called as free homotopy. And if we have this set A of X and we impose conditions like this, then this is going to be called relative homotopy. Okay, so in particular we can define the following in so instead of taking this A, so let I dot be the boundary of I in R. So the equivalence class of a path F relative to I dot is called the path class of F and is denoted by this. So basically if I have a function and now the set A in this case is basically I dot. So I dot is the boundary. So what is the boundary of this closed interval? It's 0 to 1. So basically in the relative homotopy, if we take A to be this set, then what does it says? So it says that if I have a function, let's say f naught, and this is basically f naught of 0 and this is f naught of 1, then these 2 points are going to be fixed. So in other words, this f naught is homotopic to another function f1. So f naught is homotopic to another function f1 relative to I dot if the following situation happens. So this will be homotopic so to f1 if this happens. So this is the function f1. So we are continuously deforming from f naught to f1. So these are the intermediate functions, but the point is for each and every value of t, so these endpoints are fixed. So in other words, I can say that f of, so if I take this to be 0, t0, so this is always going to be f naught of 0, which is of course equal to f1 of 0 as well. Okay, so that's one point of this set A. The second point is f naught of 1. So the same condition for each and every value of t, and x is equal to 1, this is going to be exactly equal to f naught of 1, which is equal to f1 of 1. So so basically we have defined that if A is equal to I dot, which is the boundary of the closed interval I, then this is what will happen. We are continuously deforming from f naught to f1, but the end points, so the initial and final points of the paths are fixed. Okay. So in particular we can define path class of a loop in the following way. So a loop is a very special path, so we can impose this condition, and for example if f and g are 2 loops, so let's say this is my function f and this is the loop g, and this is the point where we are having this loop. So what is this point? So this point is f of 0, and of course this is also equal to f of 1, and similarly the same point is g of 0, which is equal to g of 1. So then they are homotopic relative to I dot if there exists continuous map such that the following happens. Now if you compare these two cases, so in this case the initial and final points are different, but in the case of loops the initial and final points are the same. So basically these conditions, so these two conditions become the following, that for each and every value of t these must be equal, and since g of 0 is equal to g of 1 and g of 1 is equal to f of 1, which is equal to f of 1t for all t. So in other words, what we are saying is that for each and every value of t, so for any intermediate loop, the initial and final point of the loop are going to be the same. So for each t we will get a loop. So for example this is the loop corresponding to, let's say, point 3. So for t is equal to point 3 I will get a loop. So let's see, this is that loop. Now the initial point of the loop is 0.3 and the final point of the loop is 1.3. So these two must be equal. So that's what we are saying for each and every value of t. So 0t is equal to f of 1t. So in particular, when t is equal to 0.3, then this is what we get. So if we take any other loop, any other intermediate loop, then the same condition will be satisfied. So by taking this relative homotopy, basically we are making sure that the loops have the same initial and final point. So this point, which is going to be called base point of the loop, is very important because we want to study the loops at this point. So we want to make sure that these two loops f and g can be transformed or deformed into one another by or through the loops which have the same initial and final point. So using this concept of relative homotopy, we have achieved how to show that two loops are homotopic and all the intermediate loops have the same initial and final point called the base point. So from now onwards, unless otherwise specifically mentioned, we will take f as the path class of loop of f. So what is this path class? So this path class is basically set of all loops which are homotopic to f, and of course when I say homotopic, it means this relative homotopy, and where this set A is equal to I dot, which is the boundary of I. So in particular, in this case, A is equal to I dot is equal to 0, 1. Okay, so that's how we define two loops are homotopic, relative homotopy. Okay, so this is going to be our notation. Whenever I will write square bracket f, it means path class of a loop and not free homotopy of loop f. The set of all path classes f of loops in a space x at base point x naught is denoted by this. Okay, let x be a space, then pi 1 x x naught is a group with respect to the product this. So if I have a path class of f and path class of g, then this star operation is operated on these two path classes and it will give me path class of f star g. So we already know what is f star g. Basically we are combining these two paths. So the group pi 1 x x naught is called the fundamental group of x at base point x naught. Okay, so basically we are studying all the loops at point x naught. So using in in place of I, we can define other homotopic groups, and which is not the topic of discussion at the moment. So let's prove this proposition. So we have a collection of path classes and the base point of all those path classes is x naught, and that's the operation inside this set, and we want to show that this set under this operation is a group. Okay, so first of all we need to show that this operation is well defined. So well defined means if I have a path, let's say f homotopic to f1, of course relative to I dot, and if I have g naught homotopic to g1 relative to I naught, then I have to show that f naught star g naught, which is of course we know that is equal to f naught g star. So we have to show that this is equal to f1 star g1, which is basically f1 star g1. So why do we need to show this? So when I consider this path class of f naught, then this path class of f naught contains all those functions which are homotopic to f naught. Of course when I say homotopic, it means relative homotopic. So since f0 is homotopic to f1, then this class is the same as the class f1, because I can take any of the function from this class to represent this class. So as path classes, they are equal. And similarly, g0 is homotopic to g1, so the path class of g0 is equal to the path class of g1. So since f0 is equal to f1, so if I replace this f0 with f1 and this g0 with g1, then I should be able to get the same product in this set pi 1 of x, x0. Okay, so that's why we have to show that this product is well defined. So in other words, I have to show that these two path classes are equal, or in other words, I have to show that f0 star g0 is homotopic to f1 star g1. Okay, so let f be the homotopy and capital G be the homotopy, which is used to show that g0 and g1 are relative homotopic. So how to show that f0 star g0 is homotopic to f1 star g1? So for that we define homotopy h of x t, which is basically equal to f of x t star g of x t. So in this case, t is going to be the parameter, and when we are defining this star, this is going to be on the x's. So in other words, this is basically equal to f of 2x t, and x varies from 1 by 2 to 0, and g of 2x minus 1 t, and x varies from 1 to 1 by 2. Now let's see what is f h of x 0. Okay, so when t is equal to 0, then this becomes f of 2x 0, and x varies from 1 by 2 to 0, and g of 2x minus 1 0, and x varies from 1 to 1 by 2. So what is f of 2x 0? So we know that f is the homotopy which is used to show that f0 is homotopic to f1. So in other words, when I take x is equal to 0, then I should be able to get f0. Okay, and similarly, when I take t is equal to 0, then I should be getting g0. So basically this is equal to f0 of 2x, where x varies from 0 to 1 by 2, and g0 of 2x minus 1 0, and x varies from 1 by 2 to 1. So if you remember, then this is exactly f0 star g0. Similarly, we can show that h of x1 is equal to f1 star g1. So also this homotopy h, so this h is basically continuous, because this f is continuous and this g is continuous, and let's see if they agree on their intersection. So what is the intersection? When x is equal to 1 by 2. So let's see what will happen at x is equal to 1 by 2. Okay, so at x is equal to 1 by 2, so we have f of, so when x is equal to 1 by 2, this is basically f of 1 t, and so we know that these are the paths, and so this is basically equal to f0 of 1, which is equal to f1 of 1, and which is the same as g1 of 1 and g0 of 1, and if we put x is equal to 1 by 2 in here, then we will be getting a g 0 of t, and which is basically the same as here. So in other words, they agree on the intersection. So f is continuous, capital F, because it's a homotopy, capital G is continuous because it's a homotopy, and their intersection is basically is the same. So we can say that this H is continuous, and H of x0 is f0 star g0, and H of x1 is f1 star g1. So this implies that f0 star g0 is homotopic to f1 star g1. Okay, so we can say that this operation of special multiplication in the set pi1 of x x0 is well defined. So far we have seen that this operation of path classes in pi1 of x x0 is well defined. Now we have to show other operations if we want to show that this is a group. So for example, we have to show that it is associative, and there exists an identity element, and every element has an inverse. So that's what we have to show now, but before that we see that if I have a path f from I to x, so it's a continuous function from I to x, and if I have another function from I to I. Okay, so if I consider the graph of this phi, then this is basically something like this. Okay, so inside this box, so this is I, this is I, so the graph of phi is like this. Now if I consider this function f phi, so it's a function from I to x, and it is continuous because phi is, we have taken this phi to be continuous, and f is continuous because it's a path. So f phi is a continuous function from I to x. So by definition of a path, this f phi is a path, and if you consider that this f, so eventually we are taking the functional values of f, and but we are just changing this I in this way. So we are just changing the images of this I. So in other words, we can say that this is a reparameterization of this f. So first we were moving along this I, and now we are moving along this I. So basically we are moving along these images now. Okay, so eventually we are moving along this I. Okay, so this is a reparameterization of f. So now we will show that if we have a reparameterization of a path, then this is homotopic to the original path. Of course we need to define a homotopy for this. So we define the following homotopy. So f of x t is equal to f of 1 minus t phi of x plus t x. Okay, so since f is a continuous function, phi is a continuous function, so this composition is going to be a continuous function. So this capital F is continuous. Now let's see what is f of x 0. So when t is equal to 0, so we will get f of phi of x. Okay, so in other words, f phi of x. Now when x is equal to in general value and t is equal to 1, so what we get, so when t is equal to 1, this is basically f of x. So this function, which is a continuous function, and for t is equal to 0 it is f phi, and t is equal to 1 it is f. It is homotopy of f and f of phi. And also there is another condition on this phi, that phi of 0 is 0. So as we can see, so the starting point and the ending point are the same, so phi of 1 is equal to 1. So if these two conditions are imposed on phi and phi is continuous, then we also get the following condition, that for each and every value of t, so basically this is equal to, okay, so f of 1 minus t phi of 0 plus t0 so this is equal to f of, so phi of 0 is 0, so this is basically f of 0 is equal to, okay, so this is equal to f of 0. And similarly, if I take x is equal to 1 and t is any value, so this is basically equal to 1 minus t of phi of 1 plus t1, so which is equal to f of phi of 1 is 1, so 1 minus t plus t. So basically this is equal to f of, okay, so this is t, so t and t cancel out, so this is equal to f of 1. So in other words, we can say that f is homotopic to f phi relative to this I dot. So we know that what is this I dot, so this is equal to 0 1. Okay, so if I have a path f and if I have a reparameterization of f using this continuous function phi such that phi of 0 is 0 and phi of 1 is 1, then f is homotopic to f phi relative to I dot. Okay, so relative to I dot means these two conditions. So for each and every value of t, or in other words, any two intermediate functions or any intermediate function between f and f phi has the same value, has the same initial and final points. Okay, so a reparameterization of a function is homotopic to the original function, relative homotopic to I dot. Okay, now we are going to show that this operation is associative. Okay, so in other words, we want to show that if I have three elements, so I want to show that f star g star h is equal to path class of f star path class of g star path class of h. Okay, so in other words, what do I want to show? I want to show that this is path class of f star, so we know that what is the path class of s star path class of h, so this is basically equal to g star h. Okay, and on the other hand, we can write down path class of f star path class of g as the path class of f star g, so star h. So basically this is equal to f star g star h. Okay, and we want to show that this is equal to f star g star h. So that's what we have to show. So if we want to show that path classes of two functions are equal, we have to show that f star g star of h is homotopic to f star g star h. So of course, when I mean homotopic, it means homotopy, relative homotopy with respect to I dot. So let's see what is f star g star h. Okay, so basically this is equal to f of 2 t, where t varies from 1 by 2 to 0, and g star h of 2t minus 1, and t varies from 1 by 2 to 1. So we just use the condition on these two functions, and now we can further write it down as f of 2t, and t varies from 1 by 2 to 0, and we can further apply the definition of star on this function. Okay, so basically we should be able to write it down as g of 2 into 2t minus 1, and t varies from, so in this case now we are going to further divide this interval, so basically 1 by 2 to 3 by 4, and h of 2 2t minus 1 minus 1, and where this belongs to 3, 4 to 1. Now on the other hand, let's see what is f star g star h. So basically this is equal to the function f star g of 2t, where t varies from 1/2 to 0, and h of 2t minus 1, and t varies from 1 to 1/2. And we can further write down as, so we can apply the operation star on f and g, and we will be writing it down as f of 4t, because 2 into 2t is 4t, and we can further divide this interval into two parts. So basically from 0 to 1/4, and g of 2 into 2t minus 1, where t varies from 1/4 to 1/2, and h remains the same, h of 2t minus 1, and t varies from 1 to 1/2. So if we notice these two functions, f star g star h and f star g star h, so the first function is f, the second is g, and the third is h. And we also know that for example in this case, if I vary t from 0 to 1/2, then I'll be getting the whole function f. Okay, and similarly when I move from 1/2 to 3/4, I'll be getting this whole function g. And similarly when I move t from 3/4 to 1, then I'll be getting the whole function h. And similarly in this definition, if I move t from 0 to 1/4, then I'll be getting f. So once again this function f, and if I move t from 1/4 to 1/2, then I'll be getting this g, and t from 0 to 1/2 1/2 to 1 will be this function h. So basically it's the same function, it's the same composition of three functions, but written in two different ways. So there is a relation between these two functions, and the relation is that they are reparameterization of each other. So what is that reparameterization? So that reparameterization is equal to phi of t is equal to t/2 when t varies from 1/2 and 0, and this is equal to t minus 1/4 when t varies between 3/4 and 1/2, and is equal to 2t minus 1 when t varies between 3/4 and 1. So under this reparameterization, so we can easily see that f star g star of h of phi of t, this is basically equal to f star g star h. So basically these two paths are reparameterization of each other. So if I start from this and use this phi, then I will be getting this path. And we have seen that if two paths are reparameterization of each other, then they are homotopic. So we can say that f star g star h is homotopic to f star g star h. So if they are homotopic, then we can say that this operation is satisfied, or this equality holds. So in other words, we can say that this operation of star is associative operation. Now let's try to find identity of this set under this operation of star. So let f be a loop which is a continuous function at x0. So consider this constant function from I to x such that c of t is always equal to f of 1. Now consider f star c. So what is this f star c? Which is equal to f of 2t, where t varies from 0 to 1/2, and this is equal to c of 2t minus 1, where t varies from 1/2 and 1. So this is basically equal to f of 2t. T varies from 1 by 2 and 0, and what is c of 2t minus 1? This is equal to f of 1. Okay, so when t varies between 1 by 2 and 1. So basically we are getting the same path. Okay, so when t varies from 0 to 1 by 2, then we are getting the path f. But then when t varies from 1 by 2 to 1, then we are still at the same value f of 1. So in other words, if I have this function c which is constant, and the constant value is always f of 1, so we can say that if this is f and this is this constant function c, then when I take star f star c, then first I move along f when t varies between 1 by 2 and 0, and for the values t between 1 by 2 and 1, so I'm at this point. Okay, so for this whole half interval I'm at this point. So basically it is the same path, and this final point is repeated this many times, so eventually I'm getting the same path. So in other words, we can say that this f star c is a reparameterization of the function f, because I'm getting the same path but in a different way. Okay, so we have seen that if we have two functions which are reparameterization of each other, in precisely if we have two paths which are reparameterization of each other, then they are homotopic. So we can say that f star c is homotopic to f, and once again when I'm writing down the homotopy, it means relative homotopy with respect to I dot, which is equal to the set 1 0. Similarly, consider another constant function from I to x, and in this case c of t is equal to f of 0. Okay, now consider this function c star f. So this is equal to c of 2t when t varies between 1 by 2 and 0, and this is equal to f of 2t minus 1 when t varies between 1 by 2 and 1. Okay, so once again this is equal to f of 0. Okay, so when t varies between 1 by 2 and 0, and this is equal to f of 2t minus 1 when t varies between 1 by 2 and 1. So when I vary t from 0 to 1 by 2, then I am at the same point, which is f of 0, and when I vary this t from 1 by 2 to 1, then basically I am moving along f, and for the values of t which are 1 and 1 by 2, I am following this path, and so I'm getting this thing, and at t is equal to t between 0 and 1 by 2, I'm getting this same point. So basically eventually I'm getting the path f. So once again this c star f is a reparameterization of this path f. So in other words, we can say that c star f is homotopic to f relative to the interval I dot, so the set I dot. Now any two constant functions are homotopic. So in other words, let's say this constant function is let's say c1. Okay, this is c1 and this is c0 and this is c0. Then this c1 and c0 are equal. So in other words, their path class is the same. Okay, so in other words, I can say that this path class of constant functions serves as the identity of this set pi1 of x x0. Okay, so this is equal to f, because this is c star f which is homotopic to f, and similarly path class of f star path class of c is equal to f, because this is equal to f star c, the path class of f star c, which is homotopic to f. So basically they are equal. So now we have shown that there exists an identity in this set as well. So the final thing we have to show that there exist, so the functions are invertible. Okay, so let f be a path from I to x. Okay, so in particular it's a loop. Okay, then we can see that this function of f of 1 minus t is basically once again a loop, but this is in the reverse direction. Okay, so in other words, if this is, okay, so this is the loop f and we move in this direction, but then if I take f of 1 minus t, okay, then it will start from this point and move in the opposite direction. Okay, so this f star or f prime, which is equal to f of 1 minus t, so it will start from this point and move in this direction, because you can see that what is f prime of 0? So f prime of 0 is f of 1. What is f prime of 1? So f prime of 1 is equal to f of 0. So the initial point is f of 1 and the final point is f of 0. So we are moving in this way. Okay, so this function, so we call this function f prime. Now we will show that the path class of f has inverse f prime. Okay, so in other words, their star is equal to homotopy class of a constant function. Now consider homotopy h of x t, which is basically equal to f of x t star g of x t. So what is f x t? So basically this is equal to f of x when x varies between 1 minus t and 0, and this is equal to f of 1 minus t between 1 minus t and 1. And what is g of xt? So g of xt is equal to f of 1 minus x, and when t varies from, x varies from 0 to t, and this is equal to f of 1 minus t, and t varies from between, x varies between 0 and t. So this is x and this is also x. Now what are these functions? Now if we concentrate on this capital F, so it says that when t is equal to 0, then I am getting this function f of x. Okay, so this function, whole function f, so this represents f of x 0. So for any intermediate value of t, for example when t is equal to 0.5, then from 0 to 0.5 I am getting f of x, but from 0.5 to 1 I am just getting this one value. So in other words, for f of x 0.5, so let's say this is the direction, so I'm getting this function, so till here. Okay, so I'm getting this function, and after that value the function is still at this point, so it remains constant at this, so it is still at this thing. On the other hand, so we can say that when t goes on, and when t is equal to 1, so let's see what will happen. So when t is equal to 1, there is the interval for t is equal to 1, the interval is 0, so this point, and then when t is equal to 1, so from 0 to 1, and for t is equal to 1 we are getting f of 0. So basically it is just this one point. So what is f of x1? It is just this one point. So in other words, as the t goes on, as t moves from 0 to 1, basically we are shortening this path of f. So starting from this whole path we are reducing, so at t is equal to 0.5 we are reducing it to this length, and this length is ignored, and as we go on we are shortening the path of f. Okay, so let's see what is gxt. So for t is equal to 0, let's see what is t is equal to 0. So for t is equal to 0 we are, okay, so it is the same path f moving in this direction. So for t is equal to 0 we are not getting anything from here. So for t is equal to 0 it's between 0 and 1, and we are getting f of 1. Okay, so basically this is just f of 1, so g of x 0 is just f of 1. Okay, just this point. Now let's see when t is equal to 0.5. Okay, so when t is equal to 0.5, then basically we are getting 0 to 0.5, we are getting the reverse path of f. So we know that f of 1 minus t is the reverse path of f. So between 0 and 0.5 this is the reverse path of f, so we are moving in this direction and we are getting half of the path. Okay, so this red arrow is the direction of f, but we are moving in the opposite direction, and this is our g of x 0.5, and between 0.5 and 1 we are still at this point f of 0.5, so we are still here. So for any other intermediate value, for example x 0.5, so we can see that we will be getting things like this. So starting from here to here and then still at this point. So as the t approaches we are basically approaching this inverse function, the opposite way of f. And in this f of xt we have seen that as the t approaches we are shortening the path to 1 point, and in this case we are starting from 1 point and we are going to this. So in other words, for any intermediate value of t, so we will be getting things like this. So we also know that when we take star of two functions, then basically we are connecting the paths. So in other words, we can say that if this is the path f, we are moving in this direction, then for let's say t is equal to 0.5, so this is our g of x 0.5, and this is our function f of x 0.5. So we are shortening for f and we are starting from point and approaching this f, but in the opposite way. So this is the intermediate, or the situation when t is equal to 0.5. Okay, now this h of xt is continuous because f and g are continuous. Also let's see what is h of x0. Okay, so h of x0 is basically going to be f of x, and similarly h of x1 is going to be equal to f of 1 minus x. So in other words, these two paths which are reverses of each other, they are also inverses of each other in this group. So now we have shown that the operation star is well defined. Secondly, this operation is associative, there exists identity element, and they have inverses in this set. So this is basically a group under this operation of star, and this is a group of path classes of loops at a point x0. So let's consider an example for a convex set x in Rn. Let x0 be the arbitrary point of x. Then this pi 1 of x0 is equal to 0. So why it is 0? So let f0 and f1 be two loops at point x0. Okay, so we have two loops, let's say f0 and f1. Then f0 and f1 are homotopic by the following homotopy. So this homotopy says that h of x0, so when we take t is equal to 0, then of course we'll be getting f0 of x, and when we take h of x1, then for t is equal to 1 we will be getting f1 of x. So why this is possible and where we are using the condition convex set? So basically these paths are following the straight lines. So in other words, we are saying that for each and every value of t, use a straight line to deform this point to this point, use a straight line to deform this point to this point. So we are using straight lines to deform one path into another path. So and this is convex. In other words, all the straight lines or the straight lines joining 2 points must be contained in the convex set. So that's why that's where we are using the convexity of the set. So if it is a convex set, then any two loops at a point x0 are homotopic, and so we can say that for convex set the fundamental group is equal to 0 or is trivial. Let x be a space and x0, x1 are 2 points, then what is the relationship between pi1 of x, x0 and pi1 of x, x1? So we only hope to get a relationship if x0 and x1 belongs to the same path component of x. So if x0, x1 belong to the same path component of x, then there exists a path p from I to x such that p of 0 is x0 and p of 1 is x1. So let's say this is the point x0 and this is the point x1, then there is a path p such that this is p of 0 and this is p of 1. Okay, so also we know that p prime given by this thing, so this is p of 1 minus t is the inverse path. So what is p prime is equal to p of 1 minus t, and p prime moves in the opposite way. So if p moves in this way, then p prime moves in the opposite way. So this is the direction of p prime. Okay, so let f belongs to pi1 of x, x1. So in other words, if it has a loop at this point and moving in this direction, so if we have a loop at x1, then this function is an element of pi1 of x, x0. So what is this function? So far we have seen that we have 2 points x0, x1 of the space. There is a path p from x0 to x1, and there is a loop f at x1. So the loop means it's an element of the fundamental group of x at x1. Okay, so if I start from x0, move along this path p, move along this loop f, okay, and then come back using the path p prime, okay, then it's a loop at x0. So that's what this function is doing. So p star, so move along p, move along f, and then move along p prime. It's a function from I to x. It's an element of pi1 of x, x0. So why it is an element of this? Because it's a loop at x0, and pi1 of x, x0 is the set of loops at x0. So the map BP from pi1 of x, x1 to pi1 of x, x0 defined in this way is an isomorphism. So how to show this result? So the first thing is we have to show that this map is well defined. So how to show that this map is well defined? So if I have two elements, let's say f0 and f1, which are homotopic. Of course, when I say homotopic, it means relative homotopy, and of course if they are homotopic, then they represent the same homotopy class, and I have to show that they have the same images, because if the same element have different images, then the map is not well defined. So basically I have to show that BP of f0 is equal to BP of f1. So in other words, what is BP of f0? So basically this is equal to p star f0 star p prime. So I have to show that this is equal to this thing, star f1 star p prime. So in other words, I have to show that, so to show is p star f0 star P prime is homotopic to P star F1 star P prime. So that's what we have to show. Now of course we need to find a homotopy. So if we consider this homotopy, of course if F0 and F1 are homotopic, then there is a homotopy F. So now consider another homotopy, H of xt, defined in this way, that P star F of xt star P prime. Of course these P's are functions of x. So when t varies from 0, of course when t is equal to 0, then this is F0, and when t is equal to 1, this is F1. So P and P prime are continuous, F of xt is continuous, so this function H xt is continuous, and for t is equal to 0 we are getting this, and for t is equal to 1 we are getting this. So basically we can see that P star F0 star P prime is homotopic to P star F1 star P prime. So this function is well defined. Now we have to show that this is an isomorphism. So first we show that this is homomorphism. Okay, so BP is homomorphism. So how to show that this is an homomorphism? So start from BP of F star G. Okay, so we can write it down as, okay, so B beta P applied on F star G, so the path class of F star G. So this is equal to P star F star G star P prime. Now we also know that pi 1 of x1 and pi 1 of x0 are groups, and what are the inverses? So if I have P, then the inverse of P is P prime, so and their multiplication is constant. So basically what I have done is I have introduced this P star P inside this F and G. So basically this is equal to, so which is equal to P star F star P and P prime star okay, so this should be P prime and this should be, okay, so this is equal to P prime and okay, so P star G star P prime. So now what is this? So this is equal to beta P of F star beta P of G. So this shows that this beta P is a homomorphism. So how we show that this is an isomorphism? So consider this beta P prime. Okay, so we can easily see that beta P prime of any path class is equal to, so beta P prime, so the path class of P prime star F star P, because the inverse of P prime is P. So similarly this is equal to P star P prime star F star P prime, so the path class of this, so they are inverses of each other, P and P prime, so eventually we will get this. So this serves as an identity. Similarly we can show that BP prime beta P is also identity. So in other words, this beta P is bijective, so it's bijective homomorphism, so we can say that it's an isomorphism. So our next topic of discussion is simply connected spaces. If a space X is path connected, then the fundamental group is independent of the choice of base point. Hence for a path connected space we can talk about the fundamental group of the space. So a space X is called simply connected if it is path connected and has trivial fundamental group. So the following result explains the name of simply connected space. A space X is simply connected if and only if there is a unique homotopy class of paths connecting any two points in X. So let's see how to show this result. So let X is simply connected. In other words, it is path connected. X is path connected. And pi1 of X is equal to 0. So now notice that I'm not mentioning any base point, because according to our previous result, if the space is path connected, then the fundamental group based at point x0 is isomorphic to the fundamental group based at x1. So they have the same fundamental group at each and every point, so we can just try and write down directly pi1 of X instead of mentioning the base point. Okay, so now we have to show that there is a unique homotopy class of paths connecting any two points. So let x0, x1 be 2 points, and let f0 and f1 be 2 paths. Okay, so such that f0 of 0 is equal to f1 of 0 is equal to x0, and f1 of 0, sorry, f1 of 1 and f0 of 1 is equal to x1. Okay, so if this happens, now we have two paths between 2 points x0 and x1. Now we have to show that these two paths are homotopic. Now let's see, this is the point x0 and this is the point x1. So now this is the path f0 and this is the path f1. Okay, so also I can construct the path f0 prime, and similarly I can construct the path f1 prime. Now if we consider this f1, so starting from this point, following this f1 and then following this f1 inverse, it's a loop at x0, and we know that it's a simply connected space, so the fundamental group at every point is trivial. So in other words, we can say that this f1 prime, which is the inverse, star f1 is homotopic to C. So in other words, we can say that f1 prime star f1, so star f0 is homotopic to f0. Now similarly we can see that this function f0 star f1 inverse, okay, so starting from f0 going in this way and then coming back using f1 prime, so this is also a loop. Okay, so f1 star f1 prime should also be homotopic to C, because this f0 f1 prime is also a loop at x0, and all the loops are trivial because it's a simply connected space. Now I can say that prime star f1 is homotopic to f1. Okay, just taking star on both sides. So from this expression and this expression we can say that f0 is homotopic to f1. So any two paths connecting any 2 points in space X are homotopic. Now if this holds, that the homotopy class of paths connecting any 2 points in X, okay, so if this happens, that there is a unique homotopy class of paths connecting any 2 points in X, then of course it is simply connected, because any connecting any 2 points, let's say x0 and x1, so instead of taking 2 points I can just take loops. So set of all paths connecting x naught with itself, so they are homotopic. So of course there is only one homotopy class of loops, which is the trivial, so we can say that the space is simply connected. So next time we will be discussing the functor pi1, and we will see in detail what is this functor all about, and it will depend on this lecture's discussion of fundamental group. So this is the end of the lecture. Thank you very much, and Allah Hafiz.